Greetings! In today's video, we're going to take a look at this year's O-Level E-Math Paper 2, specifically the very last question that has spooked many students. I would also like to caveat that as this is a problem in the real-world context, it remains a relatively open problem and there is no one correct answer. So as long as you can make your argument and your answer does make sense, you should get full credit. So the problem goes like this. Someone named Chen is considering to install some solar panels at his home. He wants to estimate the total area of solar panels that he would need to generate the amount of electricity used by his household. He finds the following information on the internet. So he needs to first find the average amount of electricity measured in kilowatt hours used in one day. Next, he needs to find the number of peak sunlight hours that he will receive in one day. He's given the formula solar panel output in daily watt hours equals the solar panel watts multiplied by the peak sunlight hours multiplied by 75%. He is advised to use the same type of solar panels throughout his home. He's given the definition that 1 kilowatt hours is the energy used in 1 hour by a 1 kilowatt appliance. Lastly, he's given the conversion rate that 1 kilowatt is equals to 1000 watts. Next, he does a bit of research into the peak sunlight hours and he finds this table that gives the average daily peak sunlight hours by the months of the year. Fun fact here is that in November and December during the monsoon period, the peak sunlight hours are much lower. Next, he finds the specifications of 4 different types of solar panels summarized in this table. In part A, this is quite the giveaway question for physics students, but it's meant to help the typical student understand the relationship between energy and power. So in this question, we are told that we have a games console that has a power rating of 165 watts. And we need to calculate the amount of energy in kilowatt hours used in 5 hours by that game console. So to answer this, we need the hint in the info section that 1 kilowatt hours is defined as the energy used in 1 hour by a 1 kilowatt appliance. So instead of an appliance, we have a games console. So the amount of energy will be the power rating 165 watts multiplied by the time, which is 5 hours. Of course, we want it in kilowatt hours, so we've got to convert the watts into kilowatts. So that'll be 0.65 kilowatts times 5 hours, which gives us a final answer of 0.825 kilowatt hour. So in part B, this question wants the average peak sunlight hours, so we can refer to the peak sunlight hours graph. And first, we're going to record the monthly averages across all the 12 months in the year. Next, we are told to assume that all months have an equal number of days. So instead of taking a weighted average, we can just take the typical average. So we'll just add up all these averages together and divide it by the 12 months. And that will give us 4 and 53 over 120. But since we're just assuming that all the months have equal number of days, this is clearly not exact. So I would leave the answer in 3 significant figures. Lastly, in part C, we are given a graph of Chen's electricity use. And from this graph, we can see his cumulative usage for 4 different years, year 1 to year 4. And we need to estimate the total area of solar panels that he would need for his home. Now, this section is a little bit more open, so whatever calculations we make, we need to justify it with our assumptions. So the key idea here is that from this graph, we can work out his energy consumption that represents his energy needs. And that will tell us how many solar panels he would need to produce the energy to meet that consumption. Now I'm going to present to you 3 different models to work out his energy consumption. In the first model, we're just going to take his 4-year monthly average. And we can just refer to these 4 data points. This tells us his cumulative usage for 4 different years. So if we just read these 4 values and add them up together, we would get his total usage over 4 years and divide it by the 48 months to get a monthly average of 231.25 kilowatt hours. Now, in model number 2, we could assume that Chen wishes to live entirely off the grid. That means that he will need to be prepared to meet his highest monthly consumption. So his peak monthly consumption can be seen from the graph by finding the steepest gradient, which is here. So we can measure the amount of energy consumption that occurred in November of year number 4. So we just take the 2,750 minus 2,400. That tells us that in that month alone, he used 350 kilowatt hours. So perhaps we'll try to meet that particular need. However, I'm a far more kiasu Chen, and I think we should plan ahead into the future and forecast a monthly average at least 4 years into the future. So I'm going to assume a steady increase in the energy consumption and just estimate graphically. So based on my estimation, it should come out to about 3,600 kilowatt hours per year. So we'll divide that by just 12 months to give us a monthly average of 300 kilowatt hours that we need to plan for. So from the monthly needs, whatever number you have calculated, we can work out his daily needs and the daily output. So we'll just take that monthly needs and divide it by 30. So 30 is a reasonable average for the days of the month, and that gives us a nice target. So in my case, I have 10 kilowatt hours that I need to produce per day. Next, we'll convert the kilowatts into watts. So that comes out to 10,000 watt hour per day. Now, based on the formula that the solar panel output in daily watt hours, which is 10,000 watt hours, is equals to the solar panel wattage multiplied by the peak sunlight hours, which we calculated in part B to be 4.44 hours multiplied by 75%. Now, there's some debates here because instead of 4.44 hours, you could also choose 3.9 hours. That corresponds to the lowest peak sunlight hours during the November period. And that's also a valid assumption because if you're going for living off the grid, then 3.9 is a nice number to work with. But I'm going to go with 4.44 because that's what we calculated in part B. So the wattage of the solar panels would be 10,000 watt hours divided by 4.44 divided by 75%, which comes out to 3,003 watts. Next, we can look at the table of specification. So looking at the 4 types of solar panels, actually, why do we need the mass of solar panels? I don't think that's quite necessary because we don't exactly know the load capacity of his roof. So let's just delete away this column and focus on the important stuff. Next, we need to estimate the number of panels needed, and this can be done by taking the solar panel wattage, 3003 watts, and dividing it by the solar panel wattage for each individual panel. So let's take, for example, in type A, there'll be 3003 divided by the 3000 watts. So we'll need about 10 panels. Now, it's also reasonable for some students to round up because you could argue that you want to meet the need. So every wattage needs to be accounted for. But in my case, I think just rounding off to the nearest integer would do. So we can do the same calculation for type B, C, and D as well. So these would be the respective panels needed for each type of solar panel. With that, we can finally work out the total area for each brand of solar panel. So for example, in type A, the total area will be the 10 panels multiplied by the length of 1.46 multiplied by the breadth of 1.05. So a total area of 15.33 square meters. We can repeat this calculation approach for type B, C, and D as well. And it seems that type D is going to give us the least area. So Chen here can save some roof space for future solar panel expansions. Lastly, our conclusion. We would advise Chen to install 8 type D solar panels. This would result in a minimum total area of space used, only 14.2 square meters. Yet, these solar panels would produce almost all the energy that he would need, even accounting a steady increase of energy consumption over the next 4 years. Lastly, as an added bonus, any excess electricity that he produces can be sold back to the Energy Market Authority in Singapore, and the money that he earns can be used for the maintenance of his solar panels, as well as to purchase energy during the lower yield months like in November and December during the monsoon season. So this is my solution to this year's eMath real world question. Do you have a different approach? Do let me know in the comment section below. Thank you and have a great day of learning.